GMAX, Journal of Electrical Engineering, Mechatronic and Computer Science, ISSN 2614-4859, Volume 3, Number 2, August 2020, pp. 143-148, https://doi.26095/gmax.v3i2.4583. 143. P. Water Purification Technology Implementation Design. Angara Trisna Nugraha A. 1. Rahman Arifuddin B. 2. A. Polytechnic Perkapalan Negri Surabaya JL Teknik Kimia Surabaya 6011 Indonesia. B. Universitas Merdeka Malang JL Terusan Raya Dieng No. 62-64 Malang 65146. 1. angaranugraha@ppns.ac.id. 2. rahman.arifuddin@unmer.ac.id. Star corresponding author. 1. Introduction. Water is a basic human need. In everyday life, water is always used for drinking, bathing, washing, and other necessities. However, the availability of water still does not meet clean water standards. There are several parameters that can be used to determine water quality, namely physical parameters, chemical parameters, and biological parameters. To overcome this condition, it is necessary to have water treatment so that the water used meets the standards of clean water suitable for use. 5. Research on water treatment has been carried out by various methods, both in terms of filtration and sensors used. This research will design a more effective digital measuring instrument for measuring water parameters in terms of pH, clarity, and the use of natural filtration and water level control as an automation system. 2. Method. 2.1 Block diagram. The method of designing tools is by providing research support tools and materials in the form of hardware, pH sensor, LDR, electrotester, LCD, Arduino Uno, natural filtration materials, HCSR04, and UV filtration, and software, Eagle PCB and Arduino ID. This research consisted of several stages, namely the design of the hardware, the connection between the hardware, the manufacture of the software, the synchronization between the hardware and the software, and the stages of testing and analysis of the results. The following is the design of the water purifier hardware design. Abstract. Keywords: filtration, water purifier, pH, water level, clarity. Seeing the condition of water availability with good quality which is starting to decrease, it is necessary to have water treatment before the water is suitable for use. Therefore, in this research, a more effective digital measuring instrument is designed to measure water quality in terms of pH and water clarity. The design of tools in the form of natural filtration and pH measuring devices. This study used several water samples, namely rainwater and well water from different locations. Based on the test results, the tool works effectively with a pH value that has been in the standard range from the start, 6.5-9, after 4 times of filtration, which is between 6.82 to 7.60, so that the pH value of the water will be maintained in a condition that is fit for use. For acidic and alkaline pH categories, it requires repeated processing to get the value according to the standard fit for use. GMEX, Journal of Electrical Engineering, Mechatronic and Computer Science, ISSN 2614-4859, Volume 3, Number 2, August 2020, pp. 143-148. https://doi.26905/gmax.v3i2.4583. 144p. Fig 1 Block Diagram. 2.2 Flowchart System. The flow of the water purifier testing process is the initialization of the pH sensor, the water level sensor, the clarity sensor, the electrolysis is on, pump A is on, pump B is off, pump C is off, and the UV lamp is on. Seen in Figure 2. Design of a water purifier can be seen in Figure 3. Consists of 4 charts, namely Chart 1 as a place for input sensors and initial value taking, Chart 2 as a place for filtration materials and a water level sensor, Chart 3 to place the final input sensor. Fig 2 flowchart. GMEX, Journal of Electronic Engineering, Mechatronic and Computer Science, ISSN 2614-4859, Volume 3, Number 2, August 2020, pages 143-148, https://doi.10.26905/gmex.v3i2.4583. 145p. The following is the design of the tool as a whole. In this study, a pH sensor, HCSR04 sensor, and clarity sensor were also calibrated to obtain results that match the tools that have become the benchmark for calibration. Calibration is carried out on all sensors used. 5. Fig 3. The overall tool design plan. 3. Results and discussion. Discussion of the test results include sensor testing, Arduino Uno R3 testing, relay testing, power supply testing, sensors, and testing the work system as a whole. 3.1. Water filtration testing. Based on the results of the water filtration test from the catfish pond in Table 1, with 4 experiments, it was found that the more it was done repeatedly, the results obtained from the filtration process would be the smaller the NTU value. At the beginning of the pool water, a value of 194 NTU was detected. When the filtration process has been carried out up to 4 times, the water looks clear, so the value is 7 NTU. From the results of this test, it can be said that the value of the filtration test is effective with 4 trials. The smaller the NTU level, the cleaner the water it produces. Table 1. Water filtration test results. No. Water condition. NTU. 1. Water from catfish ponds, 194. 2. Filtered, 67. 3. Filter 2, 45. 4. Filter 3, 43. 3.2. Testing the water level sensor, ultrasonic HCSR04. Based on the test results in Table 2 and Table 3, sensors HCSR04A, HCSR04B, and HCSR04C with a predetermined distance prove that the sensor used is functioning properly and is close to the true value. 6. It can be seen from the error percentage value. GMEX, Journal of Electronic Engineering, Mechatronic and Computer Science, ISSN 2614-4859, Volume 3, Number 2, August 2020, pp. 143-148, https://doi.26905/gmex.v3i2.4583. 146p. Table 2. HCSR04 sensor test results. No. Distance measured. On ruler. HCSR04A, HCSR04B, HCSR04C. 1. 5. 5.04, 4.89, 4.96. 2. 6. 6.09, 6.16, 6.23. 3. 7. 7.14, 7.21, 7.28. 4. 8. 8.05, 8.12, 8.19. Table 3. Test results. Error percent. Sensor HCSR04. No. Error percent. HCSR04A. Error percent. HCSR04B. Error percent. HCSR04C. 1. 0.80, 2.20, 1.59. 2. 1.50, 2.67, 3.83. 3. 2.0, 3.0, 4.0. 4. 0.63, 1.50, 2.37. 3. 3.3. Testing of the degree of acidity, pH. A. pH buffer testing, 4. Based on the test results using pH 4 buffer, it can be seen in Table 4. The error percentage value is still large because the sensor is very sensitive to acid-containing materials. Likewise, the test material has decreased in quality because the test material has been contaminated with other pH when testing repeatedly, so that the results obtained when testing the pH 4 buffer were less than optimal. B. pH buffer testing 8. The results of the percent error in Table 4, the percent error results obtained show the value that has a small percent error, so that the pH value of the buffer and the pH of the measurement are also not much different or close to the same. The pH sensor in measuring alkaline pH shows the ideal value. C. pH buffer testing 9. The results of the error in Table 4, the percent obtained, show the value that has a small percent error, so that the pH value of the buffer and the pH of the measurement are not much different or close to the same. The pH sensor in measuring alkaline pH shows the ideal value. Table 4. Test results using buffer pH 4, 8, and 9. No. Original. pH. ADC. pH measurement. Error. Percent. 1. 4. 686. 4.49. 12.25. 2. 4. 666. 4.80. 20.0. 3. 4. 680. 4.70. 17.50. 4. 8. 640. 8.24. 3%. 5. 8. 640. 8.24. 3%. 6. 8. 588. 8.55. 6.88. 7. 9. 492. 9.59. 6.56. 8. 9. 447. 9.43. 4.78. 9. 9. 487. 9.72. 8%. D. Clarity sensor testing. The clarity sensor test was carried out with conditions in clean water, with 1 ml ink, 2 ml ink, and 3 ml ink. In the table, 3x data collection in the form of ADC value is taken, and the conversion result from ADC value to clarity value is taken. Based on the whole table, it can be seen that the more cloudy the water in the container, the greater the ADC value of the clarity sensor, and vice versa. The clearer the water in the container, the smaller the ADC value. GMEX, Journal of Electronic Engineering, Mechatronic, and Computer Science, ISSN 2614-4859, Volume 3, Number 2, August 2020, pp 143-148, https://doi/10.26905/GEM/CS.v3i2.4583. 147p. Table 5. Clean water sensor clarity test results. NO, ink, ADC, clarity value. 1. 2 ml 749 72.65. 2. 2 ml 753 73.04. 3. 2 ml 748 72.56. E. Testing the implementation of water purification technology design. Figure 5 above is the result of the actual tool design. The design in the first chart is used to determine the condition of the water based on the condition of the acidity and clarity values. Then proceed to the second chart, which is used as filtration to maintain or change the pH value and clarity. And the third chart is used to determine the value of the filtration result. If the results of the filtration are not suitable, it will be repeated until you get the desired value. Fig 5, Water Purification Technology Design. After testing the tool as a whole, the results of the test results show that the pH value and the clarity of the water test samples from different conditions and different places are obtained. The results of the electronic combination are then implemented in the design of the tool so that the tool works well and can take the value of the clarity and initial pH parameters, as well as the pH value and final water clarity so that a comparison of the values can be carried out both before and after being filtered. F. Testing the implementation of water purification technology with test objects. At this stage, the test results are carried out using test objects which use the independent variable in the form of water conditions that are different from places and sources. The water sample only took water in the Jember Regency area. The water used is well water, rainwater, and PDAM water. In testing the pH levels in the test sample, 4 samples of test water were taken, where water that had a high acid level to a high alkaline level and water that was already in neutral conditions from the start. The clean water quality requirements that water is fit for use are for the pH category in the range of 6.5 to 9. It can be seen in the well water in the Patrang sub-district where the water is acidic and the well water in the Muktisari area where the water is wet. The water is filtered with the same treatment, which is 4 times the results obtained exactly in accordance with the range of acidity suitable for use. Meanwhile, water that has a neutral value from the start, such as on JL Java and PDAM, the water with the same treatment is filtered 4 times, the value of the water is maintained at neutral conditions. In the test of the level of clarity, where the water condition is suitable for use, it is below 25 NTU. With the same test object and the same treatment, namely, water is tested and repeated 4 times. From Table 7, it can be seen that from the beginning the water was clean and clear. When the water is filtered, the clarity is maintained. Very sensitive to changes, especially in materials that contain acids, and the clarity sensor is very sensitive to changes in light conditions from outside. The filtration conditions will be maximized and effective if it is carried out continuously, both in terms of the filtration material itself will be clean as well as the water produced. GMEX, Journal of Electrical Engineering, Mechatronic, and Computer Science, ISSN 2614-4859, Volume 3, Number 2, August 2020, pp 143-148. https://doi.org/10.2690.5/GMEX.v3i2.4583. 148p. Table 6. Test conditions of pH levels in test water samples. No. Water sample district, Jember. pH water. Filter. pH water, filter 1. pH water, filter 2. pH water, filter 3. pH water, filter 4. 1. Air Chuka C 160 ml, 5.85, 5.98, 6.34, 6.78, 7.10. 2. Air Chuka C 460 ml, 5.32, 5.82, 6.15, 6.64, 6.98. 3. Air Chuka C 760 ml, 4.73, 5.04, 5.77, 6.25, 6.82. 4. Air Chuka C 900 ml, 4.54, 4.83, 5.20, 5.67, 6.26. Table 7. Test condition value of clarity levels in test water samples. No. Water sample district, Jember. Initial clarity. Initial clarity 1. Initial clarity 2. Initial clarity 3. Initial clarity 4. 1. Air Sumur Will Muktisari, 2.05, 2.14, 2.23, 2.31, 2.23. 2. Air Sumur Will JL Kalimantan, 2.23, 3.05, 3.14, 2.23, 1.14. 3. Air Sumur Will JL Java 2.77, 2.59, 2.49, 2.41, 2.23. 4. Air Sumur Will Patrang Dr. Sobandi 4.14, 3.23, 2.23, 2.14, 1.77. 4. Conclusion. When testing pH, the pH sensor used is very sensitive to changes, especially in materials that contain acids, and the clarity sensor is very sensitive to changes in light conditions from outside. When testing water that is in extreme conditions, namely acidic below 4.5 or wet above 9, it requires a repeated filtration process to get the value according to the wearable standard. References. 1. L. Madura, S. Conchi, M. Isabela, S. Singh, and K. Bisetti, Membrane Technology for Water Purification, Enviral.chem.let, Volume 16, Number 2, p. 343-365, 2018. 2. J. Singh, V. Saharan, S. Kumar, P. Gulati, and R. K. Kapoor, Lacase-Grafted Membranes for Advanced Water Filtration Systems, A Green Approach to Water Purification Technology. Crit.ref.biotechnology, Volume 38, Number 6, p. 883-901, 2018. 3. A. T. Nugraha, Dirty Air Filter System Using Boxed Equalizer MQ8 and MQ9 Wheeled Robot. GMAX, Journal Electric Engine Mechatronics Computer Science, Volume 1, Number 1, p. 23-26, 2018. 4. A. J. Joseph, A. M. Jacob, K. C. Manjush, and J. Kapen, Chitasan in Water Purification Technology, Green Sustainable Advanced Materials Application, 2018. 5. A. T. Nugraha, Rancang Bangun Teknologi Pemurni Air, Universitas Jember, 2015. 6. S. Sajoled, Raspberry Pi for Secret Agents, 2013.